So number 8 is sort of our last vocabulary word here, and it's not an amazingly difficult vocabulary word to come under, but I think it's really kind of cool. It most definitely ties in the stuff that we talked about in our physics class. For those of you who took our physics class in the fall. Is bit 112, or you've taken it before, and that's energy capacity. So capacity, of course, means how much can you fit into something. So in the case of energy capacity, it really is the ability to hold energy. So what we're talking about is, remember, our stress versus strain curve. I went ahead and copied it. It's over here. Here's stress on the vertical or y-axis. Here's strain on the horizontal or x-axis. And if you recall, stress has units of force per unit area. In fact, it looks like I went ahead and messed up. I got to put this value back in. Remember, it's newtons per square meter. I forgot a square there. And strain was meters per meter. It goes away. And when you multiply stress times strain, which is what this graph suggests, this is the y-axis, this is the x-axis, and when you multiply the y times the x, you take the newtons per meter, forgot a square there, I'll fix that in the download, newtons per square meter times meters over meters. What happens is we get a force times a distance, a newtons per meter. And if you recall, force times distance back in physics, that equals work, or at least the change in force times distance equals work. And work, change in work, is energy, or joules. So down here, illustration-wise, if we have a little tiny piece of material, in this case I have what appears to be a block or a brick, and you go ahead and push on it really, really hard, and you actually squish it, what you've done is you've taken a force per unit area and you've multiplied it times a distance, and the resulting answer happens to be a joule, or energy. And the question is, well, where did the energy go? Well, the answer is, I know it takes a lot of energy if this happens to be your hand squishing this, or this happens to be some huge machine or robot squishing this. This force is providing the energy. The question is, where did the energy go? And the answer is, the energy goes into that thing that you're squishing. So if we go ahead and apply a load, apply a stress, and this thing starts to strain, then the joules start to store up, or start to fill up the material you're talking about. It's almost analogous to a battery, where you would charge up a battery. You take a battery that's nearly discharged or dead, and then you add electrons into it, and now it has lots of energy inside of it. In the case of a mechanical part, if you take a spring, or in this case a little block or a brick, and you start squishing it, eventually, as it starts to move or get squished, the energy gets stored inside the mechanical part. The exact opposite is true if you take a force and you pull something and stretch it. Again, we have a force per unit area. It's moving a distance. Force times distance is work. A change in work is energy. And again, we're storing energy inside the material itself, inside the joule energy of this material. So if we go back here and take a look at this graph, what we have is we have the stress. This is the pull or the push. We have the strain. This is how long or short is it getting. But what happens is, if you take a look at this curve right here, yes, in this area it's elastic, it will snap back. In this area it stops snapping back, it's starting to get permanently longer. But eventually what you're talking about is, if you numerically look at the area underneath this curve, and we know that area is base times width, or in this case height times base. What we're talking about is the area underneath this curve is a whole bunch of joule energy. And eventually, whatever the material is that we're stretching, whether we're stretching it or we're squishing it, can't hold that material anymore. It's sort of like blowing up a balloon with so much air that it can't possibly hold it anymore. The balloon explodes. Whether you're filling it up with air or whether you're filling it with water. In this case, the material that we have, as it fills up with energy, eventually it can't contain that much energy anymore, and it explodes. And that's what causes the material to fracture or to break. So in this case, this is just the cartoon of energy versus versus this stress and versus strain. But if we go all the way back to sort of our beginning here, okay, back to this guy, recall these things broke because we put so much stress into it, so much load, and eventually it strained so much that it broke. So what happened with all these examples? Again, this piece of aluminum that snapped, this appears to be an iron pipe that has cracked. Looks like it's a rivet or it's a nail or some sort of metal metal pin that it's snubbed. This rope has exploded. This pencil has snapped. What has happened is there's been so much joule energy that was placed into these materials, they couldn't handle it anymore, and they broke. They failed. And so a lot of these materials, in this case, this is how these materials fail. The rope snaps or explodes from the middle. This nail or this rod or this pipe cracks or snaps. The pencil splinters as it falls apart. So different materials happen to react differently to how much energy they can store, and eventually they break. So obviously all semester we're going to be talking about, hey, whatever material you're talking about for your product, iPhone 6 come to mind. If you go ahead and sit on your iPhone 6 and it starts to bend, or you sit on your smartphone and you start to put too much force on the screen and it snaps and shatters, what's happening is it's now broken. And if you're selling an iPhone 6 with a broken screen or a completely folded in half or broken case, it's not very useful. So imagine all the materials that different companies have to worry about. Automobile manufacturers, gosh, my clothes, this microphone, this computer, this mouse. A lot of these materials that you sell to somebody or that you use, we want to make sure that we know what their mechanical properties are so that they don't literally explode or crack or break while our customers are using them. So let's run all the way back down here to where we were before, and that was this guy. So here we are, this last idea of energy capacity, and then that sort of rounds out our 8 vocabulary words. 8's not a magic number; it just happens to be the vocabulary that we need to start off this course. And again, just as a review, we're talking about the mechanical strength of a material. How strong is it? We measure how strong something is by pushing or pulling on it. That's why it's called a mechanical property. It's a machine. That's going to give us values of stress. And again, the units are force per unit area. When we do stress something, it's typically going to move. Even if it's a small move, it'll move. Large steel locomotives and iron locomotives and steel rails move really, really small compared to floppy rubber bands, but they do move. We're going to measure the strain, how much does it move, and then we're going to be able to define what happens when it does move. If it moves really, really easily and it doesn't break, we call that plastic or plasticity. If it happens to move and snap back when you're done moving it, that's elastic. If it's very difficult to move, then we say something is very stiff. If it's very difficult to scratch the surface, we say something is very hard. And then again, we talk about this energy capacity. When does the material just give up the ghost and can't possibly do it anymore? So with that, I'm going to snap back to me. That's our opening material for materials, the ISBIT 212 materials course. We're going to need to get a handle on these 8 vocabulary words, and then we're going to be using these vocabulary words throughout the semester. And then, of course, if you ever happen to have a career or happen to work in a project that's dealing with mechanical properties, you're going to use these values all the time. So I'm looking to press the button here to stop, and we'll see you on the other side. Thanks, guys.